Okay, this is the second part of a question that I started before, but let's get through it. Okay, so hydrogen atoms and oxygen atoms chemically combine to produce water molecules. Complete the figure below. It's actually on another piece of paper, I'll grab that in a second, to show the arrangement of the outer shell electrons of the hydrogen and oxygen atoms in a molecule of water. Use dots or crosses to represent the electrons. So first we've got to remember what the question says. Let's make sure we use dots and crosses to represent the electrons. It sounds simple, but some people forget it. Okay, so here we are. There's your typical diagram that you have to fill in. So when we're filling this in, we've got to remember how many electrons each of the atoms has in its outer shell. Hydrogen has 1, oxygen has 6. Now this is how you answer your question about that covalent bonding. So each hydrogen obviously has to have its electron in the outer shell, and the oxygen shares 1 with each of them, leaving the oxygen with 4 that are not involved in any of the bonds, and we draw the 4 in 2 pairs like that. So I've used the crosses for the hydrogens and the dots or the coloured circles for the oxygen. So each hydrogen in a covalent bond has 1, 2 electrons if you include the shared one in the outer shell. That one has 2 in the outer shell as well. And the oxygen, let's check we've got 8 to make sure we've done a full covalent bond. 1, 2, 3, 4, 5, 6, 7, 8. The oxygen has 8. So there we are, that's a stable molecule right there. Name the type of bonding in a molecule of water. Well, we know it's covalent. The reason we know it's covalent is because they're shared and because there's no metals involved in the bonding. Next question. Why does pure water not conduct electricity? Now at this point, if you're asked about not conducting electricity, a lot of people straight away start thinking about delocalized electrons, which is great if you're talking about solids. But when you're talking about liquids or things in a molten state, you want to stay away from that answer of delocalized electrons, and you want to remember that it's ions that carry charge in molten or liquid things. Water has no ions. It's made up of the molecules, there's no ions, so we simply write water has no ions to carry the charge. Next, a couple of questions on nanoparticles. Nanoparticles of cobalt oxide can be used as catalysts in the production of hydrogen from water. How does the size of a nanoparticle compare with the size of an atom? Now when we're answering the question, let's make sure that we compare them, because that's what the question wants us to do. It doesn't ask for any specific sizes, although you can put those in if you know, but let's just do a simple comparison. Atoms are smaller than nanoparticles. We know nanoparticles are small, but atoms are the smallest that you can get, apart from, of course, the subatomic particles within the atom. Atoms are clearly smaller than nanoparticles. Finally, suggest one reason why 1 gram of cobalt oxide nanoparticles is a better catalyst than 1 gram of cobalt oxide powder. Well, the cobalt oxide nanoparticles have a larger surface area than the powder. They're ground up extremely fine, and when you're talking about catalysts, it's the surface area that's an important thing. So we've answered, even though the mass is the same, it's the surface area that makes them the better catalyst. Okay, see you soon.